and I'm elated to present our work, Scenic Routes with Weighted 2D Points, in the International Geometry Summit 23. The abstract. So in a given 2D space, we can have points that have different levels of importance. One would prefer viewing those points from either a closer or farther position in accordance with their level of importance. The point in 2D from where the user can view two given points in accordance with his or her preference of distance is termed as a scenic point. So we developed the concept of a scenic path in 2D space with respect to 2 points which have weights associated with them. Subsequently, we propose algorithms to generate scenic routes a traveler can take, which can cater to certain principles which define scenic routes. So following are the contributions of this paper. So mathematical formulation of what a scenic point constitutes, introduction of scenic routes formed by such scenic points in two-class point configurations in 2D spaces, and scenic route generation algorithms that fulfill certain defined requirements, which we'll be discussing further. An example of a metric that may determine the scenic importance of a point could be the perceived heights of major landmarks present at the point. A viewer may want to view two landmarks in such a way that the apparent height of those two landmarks are the same, so that one landmark does not dominate the other in the view. For example, consider the following photograph. We can see that the Statue of Liberty monument and the 30 Hudson Street building, that is the one on the extreme right, are nearly the same size. The photo composes both monuments in the frame without any one of them significantly overpowering the other. Note that the building on the right is about 238 meters tall, whereas the Statue of Liberty monument is only 93 meters tall. Working on the metric of apparent height discussed in the previous slides, the apparent height of an object depends on the visual angle it subtends at the human eye. It is directly proportional to the tangent of the angle that it subtends. Calculating the angle and simplifying it with some approximations, we get that the tan of the visual angle that is subtended is approximately equal to the height of the landmark divided by the distance of the person from the landmark. So now for two objects to have the same apparent height, the visual angle subtended by them should be equal. So applying this condition, we get the following formula, where W1 by D1 is equal to W2 by D2, where the W1 and D1 are the heights and the distance of the first object from the human, and W2 and D2 are the heights and the distance of the object from the second person. Let us take 2 points P1 and P2 with weights W1 and W2 respectively. A point P is said to be a scenic point with respect to points P1 and P2 if it satisfies the aforementioned conditions. So now on expanding the condition, we would get the locus of the point P, which would give us a scenic path. So now simplifying the equation, we arrive at this particular formula for the locus. Clearly, the given formula indicates that the locus of the scenic points is either a circle when delta is not equal to 1, and when delta is equal to 1, that is when the weights are equal, it is the perpendicular bisector of the line segment P1, P2. Scenic routes have a certain set of requirements, and the algorithms devised in this paper prioritize the requirements in the following order. Completeness. The route provided by the algorithm must allow one to have a view of all the given red-blue pairs. Only scenic edges. The route must consist of only scenic edges. Minimal route length, it is self-explanatory. Minimal repeated edges. A route must contain a minimal number of repeated edges. So edges which must be traveled more than once to complete the entire route. So minimal number of edges, which is again self-explanatory. We'll be talking about the scenic route algorithms that we have introduced as a part of our work, which help us generate scenic routes that satisfy the previously discussed requirements in the given order. For all the algorithms, I will be using this synthetic graph as an example to describe them. So this scenic graph is constructed with 3 red points and 3 blue points as input, arranged in an alternating fashion with varying weights. So we have introduced 3 new algorithms: the all-curve umbrella algorithm, the all-curve convex hull algorithm, and the dense point expansion algorithm. The all-curve umbrella algorithm and the all-curve convex hull algorithm work on the set E, that the set comprising of the shortest edge belonging to each scenic path, and the set S, which is the set of all endpoints of all edges E that belongs to the capital E. So the algorithms work with this set of edges E. Since the endpoints of each edge are common intersection points between two or more curves, we are trying to enable the traveler to easily switch between scenic views with minimal traveling distance by using these edges. In the ACU algorithm, what we essentially do is we take all the shortest edges from each scenic path, calculate the centroids of the points in the graph, and arrange the edges E in a circular manner around the centroid. So for example, if we take this graph on our right here, so the centroid of those edges would lie somewhere here. So we would be arranging these edges in a clockwise or anti-clockwise manner around the centroid, just so that we can connect them in a cyclic manner. We would repeat this set of steps twice, once in a clockwise order and an anti-clockwise order, and then pick the shortest route out of these two. Now the ACCH algorithm is a bit simpler. We generate the convex hull of the set S. We connect every two consecutive points in the sequence of the convex hull using the edges specified by the all pair shortest path between each of these points. And in case we have some disconnected components, for example, after creating the convex hull, this particular set of edges here was disconnected. So we connect them using the APSP yet again to the convex hull path that was initially generated. The yellow lines that we see here are those extra edges that are being added to connect these disconnected components. The dense point expansion algorithm, however, uses the points with the highest degree in the graph. So, a point with a high degree basically means that it is a junction between multiple scenic paths, and the DP algorithm leverages this particular fact. So what it does is it picks the point with the highest degree in the set of points in the graph, and for each edge terminating at that point, it checks if the edge lies on the curve already covered by an edge in the set capital E. The set capital E is initially an empty set. If not, it adds the edge to E and adds the point I naught and the other endpoint of the edge in S. We keep repeating step 1 until we select at least one edge from each scenic path. Then finally we generate the convex hull of the set S, that is the endpoints of the edges in set E, and we connect the consecutive points in the convex hull sequence using the APSP specified path. If disconnected components remain in the new graph, we connect each disconnected component with its closest disconnected component using APSP until the entire graph is connected. Let us now discuss the results of these algorithms with respect to the requirements that were listed previously. So all algorithms have been designed to satisfy completeness, that is requirement 1. All algorithms have been designed to satisfy requirement 2, that is only scenic edges as well. But this only happens if the graph is completely connected. The algorithms would incorporate edges generated in the SCBA algorithm otherwise in order to satisfy requirement 1. The ACU algorithm performs better in minimal route length with no clear winner between the ACCH and the DPE algorithm. As far as requirement 4, minimal repeated edges goes, the ACU algorithm performs better with the ACCH algorithm at second place. The ACCH and DPE algorithms perform better than ACU algorithm in requirement 5, that is minimal number of edges. Here are some results of a scenic route algorithms applied on some synthetic graphs. So from these graphs, it is evident that the ACU algorithm performs better in the minimal repeated edges criterion, since the ACU algorithm tries to find the shortest route between any two given edges. However, the ACCH and the DP algorithm work with the convex hull of the entire set, and there would be multiple edges that lie within or outside the convex hull, which have to be attached to the scenic routes via multiple auxiliary edges like these that are shown in gold. However, the ACCH and DP algorithms perform better than the ACO algorithm in the minimal number of edges criteria, because these algorithms are designed to give the user a view of all scenic pairs with minimal route switches, due to which we had to work with the convex hull of the entire set. There are some real life examples where we take our points of interest to be certain landmarks and their weights to be the height of the landmarks at those points. With these weights and coordinates, we have created scenic graphs and applied scenic route algorithms to generate scenic routes. In our work, we introduced the concepts of scenic points, scenic paths, and scenic routes in two-class weighted point configurations in 2D spaces, a characterization of the properties of a scenic route, and an analogy of these conditions in a real-world scenario. We presented three algorithms to generate scenic routes and analyze the routes generated by these algorithms. We finally pick up some real-world scenarios for which we generate scenic routes. Our paper presents a preliminary idea of what a scenic point, path, and route are. Further work may involve placing scenic points in a 3D space, new alternate definitions of what may constitute a scenic point, additional constraints on scenic routes, and alternate algorithms that may focus on a different set of requirements. Thank you.